All right, welcome. It's my pleasure to introduce today Ravi Chugh, who's finishing his Ph.D. at UC San Diego. He's been working in the area of programming languages, including this little language called JavaScript that was designed to run dinky little scripts on your web page and is now pretty much running most of the things you care about in your web browser. And he's going to tell us about some of his work to verify that code and make sure it's a little higher quality than we've come to expect. Ravi.
Thanks a lot, Dan. So I'm really thrilled for this opportunity to be here and meet many of you and tell you a bit about my work on statically verifying programs that are written in web scripting languages. But before I start, I'd like to invite you to, of course, please feel free to interrupt me and ask questions throughout the talk. So we rely more and more on the web for our everyday lives to do everything from banking to shopping, social networking, taking classes, etc. But if we take a look at the foundations upon which these applications are built, they're really rather shaky. So a lot of things can go wrong because of the so-called scripting languages that are used to write these applications, and because we run code from so many untrusted sources. So as these applications continue to become larger and more important, I think we need to develop more rigorous software foundations for the web. And in particular, in my work, I've developed static type systems that harness the expressive power of logic to precisely reason about the many tricky features in dynamic scripting languages like JavaScript. So in today's talk, I'll paint a pretty high-level picture of the challenges that we face, and I'll explain why my recent work is an important step towards this goal of a rigorous foundation for the web. OK, so let's start with a very brief history of the web. So in the early 90s, the web was little more than a bunch of static pages of text that linked to one another. And then in the mid-90s, we got the ability to add client-side code to our pages as well. So for example, in addition to the HTML that defines this login form here, we could add the following bit of JavaScript code. So here we define a function that will be called when the user clicks the login button. And the first thing the function does is check to see whether the content of the password box is empty. And if it is, it says, hey, user, you need to enter a password first. And otherwise, it goes on with processing the request. So the idea here is that the developer knows that the server definitely rejects empty passwords. So better to do this error check on the client and avoid this unnecessary round trip. So adding JavaScript to do small things to our web pages like this can be rather handy. And so indeed, in the mid-90s, when Netscape designed JavaScript, the intention was for it to be an easy-to-use scripting language as a companion to Java. So what is a so-called scripting language? Basically, it just means a dynamic language, a language with no static types. And so instead, dynamic features arguably make it easy to rapidly prototype and experiment with code. But if we fast forward to today, every time we check our email, we're actually running hundreds of thousands of lines of JavaScript. And not only that, these are code bases that changes really quickly. So it's really no longer the case that we're just doing small-scale scripting with scripting languages like JavaScript. So to get a sense for how popular JavaScript is, here's a list of the most frequently discussed languages on the popular programming forum Stack Overflow. And you'll notice that JavaScript is right up there with the heavy hitters like C# and Java. Furthermore, languages like PHP, Python, and Ruby are also really popular. And these are also scripting languages that are particularly popular for server-side web development. So the fact is that JavaScript is here, and it's here to stay, whether or not we like it. But it gets even worse. Because when we run JavaScript to do things like banking and shopping and news, we're actually running a whole bunch of third-party JavaScript as well. So to start, these applications use advertisements to pay for their services. And then we, the users, go and install additional third-party apps to further augment the functionality of our devices. So not only are we surrounded by JavaScript, we're surrounded by third-party JavaScript. So what was intended to be an easy-to-use scripting language is now being used to define massive, critical applications with code from a bunch of untrusted sources. And as I'll tell you about in this talk, JavaScript, the programming language, is much harder to reason about than traditional languages like Java and C#, which makes it even harder to ensure reliability and security. OK, so as an example of how we encounter some of this untrusted code, let's consider a simple browsing scenario. So say I'm reading the New York Times, and I see a whole bunch of advertisements and menus. And the article I'm trying to read has a link to an article in the New Yorker. And so I decide to open up this article, which fires up a new tab with, again, more advertisements, more menu items. And now I'm getting a bit annoyed that the article I want to read is a really small part of the screen real estate. And so I think to scroll down on the page and open up the article in print mode instead. And so the effect is that now the same article is shown to me, but with this extra printable equals true parameter appended to the end of the URL. And so this time, all I am shown are the contents and the photos of the article, and the advertisements and the menus and everything are hidden from me. And so this is more like it. This is what I wanted. And so I think to myself, well, it would be nice if I could open every New Yorker article in print mode like this by default. And so it turns out that every modern browser offers an extension framework that allows third-party developers to customize the browser to do things like this. So for example, we can define a print New Yorker extension that has the following bit of JavaScript code. So here we iterate over all of the elements on the document, looking for link elements, signified by the anchor or the A tag. And then for each one of these links, it checks to see whether the URL, which is stored in the href attribute, starts with the string newyorker.com. And if it does, this extension goes in and rewrites that link to contain this extra parameter printable equals true at the end. OK, so the effect is that if I've installed Print New Yorker on my particular machine, and I'm browsing some arbitrary document that has a link to the New Yorker on it, this extension will go in and rewrite that link to contain this extra parameter at the end. OK, so in addition to being able to modify the document, browser extensions can access other sensitive APIs on the client browser. For example, the network manager to make requests to download additional code and data at runtime, a facility for local storage to store things like passwords and the user's browsing history. There's also the JavaScript engine, which can be used to parse and evaluate more code, and other sensitive APIs like this. So while it's great that extensions have access to such a rich set of APIs, what prevents an evil extension from going in and rewriting all of my links to evil.com? Or what prevents a buggy password manager from reading and writing my passwords like I want, but then accidentally leaking it over the network to some untrusted server? So later in the talk, I'll explain how existing browser security mechanisms fail to give us this kind of control that we want. But at a high level, we can imagine trying to enforce JavaScript security in one of two ways. One is to dynamically check an extension at runtime and stop it right before it tries to do something dangerous. But unfortunately, dynamic checking can be expensive and lead to unacceptable performance overheads at runtime. But worse, dynamic checking misses certain classes of attacks. So runtime is simply too late to track certain kinds of security properties like implicit information leaks. Furthermore, dynamic checking can blame the wrong party, because if a clever and malicious extension plants a trap somewhere on the page, and then a benign extension later walks over it, it's going to get the blame instead. So what we would much prefer is to statically verify that a program satisfies some security property before ever running that program. And so as a first step towards this goal, in my recent work, in my dissertation, I've developed static type systems for dynamic languages like JavaScript. So traditionally, static type systems offer three promises: improved reliability and security, better development tools for programmer productivity, and improved performance. And so I'll talk about how my work will lead to each of these three directions. But first, you might ask, well, why even worry about dynamic languages? Wouldn't we be better served if we just threw JavaScript away and started with your favorite better language? But I'd argue that that's not the case, that many of the hardest challenges of the web, like dynamic content and loading untrusted code, are really independent of language. And so instead, by solving these challenges in the context of JavaScript and existing web technologies, we can improve the chances that we'll have impact in the long term. And this is the approach that I've taken with this work. Furthermore, as I'll show you, the new kind of static reasoning techniques that I've developed are general and can be applied to traditional statically typed languages as well. OK, so I'd like to spend a minute or two on a very high-level overview of what static type systems are and how they can possibly help us. So static types are used to describe sets of runtime values, things like the set of integers or booleans, or the set of objects that have a particular field foo. Fancier type systems can track things like the set of pointers that are definitely non-null, and even security-oriented concepts like the set of string URLs, which are safe for a user to visit. Now, equipped with these sets of runtime values, a static type system prevents certain classes of runtime errors from occurring. For example, trying to multiply an integer in a Boolean, trying to read a foo field from an object that doesn't have it, trying to dereference a null pointer, or even trying to redirect the user to a malicious URL like evil.com. So as a flavor of how static type systems do this, for every function f, they track what is the set of expected or required arguments. And then for every call site, what are the actual arguments x that are passed in? So each of these sets of values is described by a type, and if the system can prove that the set of the actuals is a subset of the expecteds, then it guarantees that the function call does not produce an error at runtime. On the other hand, if the system cannot prove this subset check, that means the function may or may not produce an error, and to be safe, the type system statically rejects the program. So the key idea in my work is to build on something called refinement types, where types are described using logical formulas. So for example, we can describe the set of the actual arguments as the set of values x that satisfy some formula p, and we can describe the expecteds as the set of x that satisfies some formula q. So with this perspective, now this subset check boils down to, does the formula p imply the formula q? And this is really the source of expressiveness that refinement type systems provide. Now, refinement type systems have been studied for decades, and in general, they allow the type system to refer to formulas p from some refinement logic. Now, the first key technical innovation in my work is to allow the logic to refer back to the type system, something I call nested refinements. And as I'll explain, this is one of the keys to encoding the many tricky dynamic features in languages like JavaScript. So to get a flavor of how my work fits into the research on static reasoning, at one end of the spectrum are type systems, which track relatively coarse-grained properties, but are intended to be lightweight enough to be read and written by programmers. And at the other end of the spectrum are more heavyweight verification techniques like Hoare logics, model checking, et cetera, which can track much more fine-grained properties, but aren't really intended to be user-facing systems. So refinement type systems extend the expressiveness of type systems by using logical formulas. And in my work, I developed several additional refinement type-based techniques to handle the challenging features in languages like JavaScript. OK, so far I've talked a lot about why JavaScript and scripting languages are important. Next, I'll talk a little bit about what are some of the tricky features in JavaScript that make reasoning so difficult. And then I'll describe some of the techniques in my recent work that overcome these challenges. Then I'll talk about how to start to track fine-grained security properties for JavaScript programs using this infrastructure. And I'll wrap up with a number of directions for future work. So before I continue, are there any questions at this point? So what are some of the challenging features in JavaScript? And in this talk, I want to focus on just two of the challenges. And so the first is something called lightweight reflection. And so for this, let's consider the following function negate that takes a single argument x. Now, the first thing the function does is checks to see what is the type of x. Now, the type of operator in JavaScript allows the program to reflect at runtime on what the shape of x looks like. Now, remember, JavaScript doesn't have any static types. So instead, if we think of the set of all runtime values, we have things like numbers and integers, which we can describe by the string number. We have the booleans true and false, which we can describe with the string boolean. We have objects with various keys and bindings, which we can describe with the string object, and so on and so forth. And so what this type of operator returns is one of these strings, or tags, which can be thought of as a shallow description of the type of this value. OK, so in the case that the type of x is number, negate computes the numeric subtraction of x. Otherwise, if type of x is not number, it computes the Boolean negation of x. And so the intention here is that the function negate is called with an argument whose tag is either number or Boolean. And the argument x will be used at operations of different types, depending on this runtime control flow. And so this path sensitivity on different branches is not something you find in more traditional type systems, for example, as in Java or C#. A second major challenge in languages like JavaScript stem from their notion of objects. So in particular, the field read object.f in JavaScript really means look up the string f in some dictionary of values where we have some arbitrary set of string keys, where statically we don't know exactly what that dictionary is storing. So in traditional static type systems, dictionaries are also called hash tables or maps or associative arrays. And the difference is that typically for these data structures, you don't know at compile time what the actual keys of this data structure are. So as an example that takes advantage of this notion of dictionary objects, consider the following function dispatch, which captures a typical object-oriented pattern, where given a table of methods and an operation or a method to invoke, dispatch retrieves the method and then applies it to the rest of the arguments. Now let's say we define a table of integer operations, plus and minus, both of which are some binary functions on numbers, and say we try to call dispatch with this integer table and the key star. So notice that star is not one of the operations in this table. And so when dispatch tries to retrieve it, it fails the key not found error at runtime. And so what went wrong here is that the dispatch function expects that the table object have a key called op. And furthermore, that key should bind a function on numbers. And so what's challenging here is notice that the type of table refers to one of the other arguments to the function, op. And so this kind of dependency between the types of values is not something you find in more traditional type systems. Now, there are several additional challenging features in languages like JavaScript that I don't want to dwell on in this talk, but I'll mention them in case some of you are familiar with the language. And if you're not familiar with JavaScript, don't worry about it. You'll probably sleep better tonight not knowing about all the kind of hairy details. So in addition to objects being dictionaries, they're also extensible in that keys can be added and removed at various program points. Furthermore, the notion of inheritance in JavaScript is based on something called prototypes, which is a dynamically computed form of inheritance, which is trickier to reason about than statically declared classes, for example. And it turns out that the semantics of arrays in JavaScript are also a bit weird. And so unfortunately, any analysis for JavaScript has to take into account the corner cases of arrays because every real program uses them. And so while I won't dwell on these features, I do want to point out that prior work on trying to statically reason about dynamic languages have not addressed the challenges that the object and array data structures present. So next, I'd like to talk a little bit about the techniques in my recent work that overcome these challenging features. So to start, recall our notion of the set of all runtime values. And we can describe the set of the numbers as those values x, such that the tag of x is exactly equal to the string number. Similarly, we can describe the Booleans and the objects. But using refinement types, we're not restricted to this coarse partition that's induced by these runtime tags. We can identify more specific sets of values. For example, not only the numbers, but those numbers that satisfy some extra predicate called integer. Or more specifically, the set of integers that satisfy the predicate positive integer. Or if we need to, we can even identify a singleton set, for example, the set containing only the value true. So in general, we can use a refinement type of the form x such that p to carve out some arbitrary set of these runtime values. So if we recall our notion of trying to check that a function call is safe, for example, because the set of the actuals is represented as some refinement type x such that p, and the expecteds are represented as those x that satisfy q, this subset check boils down to, does the formula p imply q? And so this notion of subtyping as being the same as logical implication is really the key enabling feature of refinement type systems. So now let's see how to start to use refinement type systems to handle some of these tricky features in JavaScript. So to start, let's return to this negate function from before. And the first thing to note about dependent JavaScript is that the programmer writes down a function type annotation inside comments before the function, and then the system tries to check, does the function actually satisfy this specification? The second thing to point out is that although all values are described by refinement types, we'll often use syntactic sugar to represent more commonly occurring types. OK, so to analyze this function, let's first consider the then branch of the negate function. And in particular, the kind of operation that we need to consider is this subtraction, which requires that the tag of x is number. Now, because we're on the then branch of this conditional, because we know that this evaluates to true at runtime, we know that the tag of x definitely is number. And so if we ask the corresponding implication, we see that, yes, this is a valid implication. OK, so next let's talk about the else branch. This time the operation to check is this Boolean negation, which requires that the argument x have tag Boolean. Well, this time, because we're on the else branch of the conditional, and because of the annotation on the argument to this function, we know that the tag of x is definitely not number, and that it's definitely number or Boolean. And so by combining these two facts, we see that on the else branch, the tag of x definitely is Boolean. And so it is being used safely as a Boolean on the else branch. OK, so what's going on here is that x is being used as a value with different types on different branches, depending on the runtime control flow of the program. And by using logic and refinement types, we can capture this kind of path sensitivity within the type system and reason about how x is used on different branches. Now, the next thing to check is, well, is the return value a number or a Boolean? And we can see that both return values certainly satisfy that type. But more interestingly, the programmer could write down a more specific return type. In particular, that not only is the output y a number or a Boolean, but it's such that the tag is exactly equal to the tag of the input. Now, again, we can check this specification. And notice here that by using logic, we can enable that the types of values can depend on other values. So for example, the return type here depends on the particular argument x that's being passed in at a specific call site.
How did you actually know that x was a Boolean?
So the question is, how do we know that x is a Boolean? So going back to this previous slide, we see that on the else branch, we know that the guard must have evaluated to false at runtime. And so we know it's not a number. And given the argument type that the programmer has written down for this function, so we are trying to verify this. So this is a specification, a candidate spec that the programmer writes down. And the system is checking, well, does this function actually conform to that spec? So given that the programmer has written down that spec, that means that the type system will enforce that the function is called only with values that are number or a Boolean.
Okay, so there's some other analysis that say that you can assume when you're analyzing this that the spec is followed.
That's right. So that's exactly how type systems proceed in this kind of modular fashion. They make these assumptions about the arguments, check this function locally, and then at calls to the function, the call sites would have to prove that what they're passing in conforms to this input condition. OK, so this is a little bit about how refinement types can track this kind of runtime control flow. Next, let's talk about how to use refinement types to handle this challenging form of dictionary-style object. Now, to start, let's consider the set of all objects that have various keys and bindings, all of which we can describe as the set of values whose tag is object. Now, more specifically, say we wanted to identify those objects that have a particular field, we can use a predicate called has to require that these objects have a key called f. And furthermore, we might say that not only should the objects have a key f, but when you select that key, what you get back is a value whose tag is number. And again, we can identify a singleton object if we need to, for example, by saying when you select the f key, you get exactly the value true. And furthermore, the domain of the object is just the set containing f. So there aren't any other keys in this object besides f. So let's see how to use refinement predicates to handle this dispatch function from before. So we can say that the dispatch function has the following type, that given an object table and a string op, such that the table object has the op key. And furthermore, when you select the op key, what you get is a function that takes two numbers and produces a number. And notice here we're defining the type of op, but we're referring to one of the other arguments to this function table. So we're expressing this kind of dependency here. And then given two numbers I and j, what dispatch eventually returns to you is a number. OK, so I've written out this specification in gory detail. But again, using syntactic sugar, we can write down a much more concise, readable type that we would expect to be understandable. Now let's return to this problematic call from before, where given a table of integer operations and a call that tries to retrieve a non-existent key, well, this time the star argument here is an op such that it's exactly equal to star. But from the argument type to dispatch, what was expected is that the integer operations table has this key. So if we ask, does this corresponding implication hold, we see that it doesn't. And so in this way, the type system rejects this call to dispatch because it fails with this key not found error at runtime. OK, so that's a flavor of how to use refinement types to handle some of these challenging features in languages like JavaScript. Next, I'd like to talk a little bit about what are some of the key ideas in my work that are kind of new with respect to prior work on refinement type systems. Now, prior work on refinement types have been able to handle the kind of lightweight reflection that I've shown you in the negate example, but have not been able to handle the kind of dictionary-style objects in the dispatch function. Furthermore, I briefly mentioned several other challenging features of JavaScript that are also not addressed by prior work on refinement type systems. And in my work, I've presented several new technical devices to overcome these challenges. But in this talk, I'll focus just on this first one of handling dictionary-style objects. Now, remember that I've said several times that the kind of key enabling power of refinement types is that subtyping is boiled down to logical implication. But it turns out that representing function subtyping as logical implication is not so easy. And so to demonstrate why, let's consider the following call to the function negate, where we pass in a number 17. And then the output of this function is used at the operation plus 42. So the intention here is that this function have type num arrow num. So in particular, the type is the set of functions f that have type num arrow num. But what we have here, this negate function, was given some different type from before involving numbers or booleans. And so the question is the type of negate a subtype of num arrow num? And so as usual, we would like to prove this subtyping relationship by asking, does the corresponding implication hold? But now the challenge is, how do we actually prove such a formula? And the challenge is that we're referring to the type system inside a logical formula, and it's not clear how to encode what the type system means using any known logical theories. And so in particular, prior refinement type systems avoid this problem by simply disallowing function types from appearing inside formulas. OK, so to dig in a little bit further, prior refinement type systems split values into two categories. So base values, or non-function values, which are described with formulas from some refinement logic P. And then a second category of function values, which are described by arrow types T1 and arrow T2. Now, as much as possible, we try to stick to decidable theories, something called satisfiability modulo theories, because for decidable theories like this, we can ask an SMT solver questions like, does some formula P imply Q? OK, so the kind of prior state of the art in trying to apply refinement types to dynamic languages effectively uses the following refinement logic. So in addition to Boolean connectives, we have the decidable theories of equality, linear arithmetic, uninterpreted functions, and McCarthy operators. And using a refinement logic like this, we can start to make good progress towards some of these challenging features in JavaScript. So for example, we can talk about unions of types, like num or bool, and track the kind of lightweight reflection that we've seen in the negate function. And we can also start to talk about the dictionary style objects with dynamically computed keys, because we can talk about some program variable k as a key. But it turns out that we can't actually talk about functions that store, dictionaries that store function values. Because say, for example, we want to talk about some binding that is a function. We can say that when you select that binding, what you get has tag function, but we can't say anything more specific about the type of this function, because the refinement logic has no way of referring to the type system. And so this is kind of a non-starter for practical purposes, because every realistic language will have dictionaries or objects that have functions, have methods in them. OK, so what we really want is a way for the type system, for the refinement logic, to refer back to the type system without giving up this property of decidability. And so this is the kind of key that the nested refinements provide. So in particular, in a nested refinement type system, all values are described using refinement types, x such that p. And then we allow the refinement logic to refer back to the type system in this way. So in addition to the type system referring to the logic can refer back to the type system, something called nested refinements. And this gives us the kind of language that we want for talking about dynamic objects that have functions inside them. But the kind of key challenges are, well, how do we actually encode the type system in a decidable way? How do we retain the kind of precision that we want in our analysis? And how do we prove that what we've done here makes any sense? So I'd like to talk about the intuitions for each of these three challenges without any Greek symbols or anything, with just kind of high-level pictures. OK, so with respect to the encoding, we treat the type system as an uninterpreted predicate in the logic, meaning the logic doesn't understand anything about what the type system means. And furthermore, these function types are treated as uninterpreted constants in the logic. So these are just some blue and yellow constants that the logic doesn't know anything about. But then in the type system, we remember that, well, we associate certain function types with these different constants. So if we were to ask the SMT solver, does this particular implication hold, it's going to say no, because blue and yellow are different constants. So this is trivially decidable, but this is exactly the kind of implication that we wanted to support. So instead what we do is, when we have a goal of the form, some function t1 arrow t2 on the right-hand side, and some arbitrary refinement type f such that p, we break up this obligation into two phases. So in the first phase, we ask, is there some different blue function type s1 arrow s2, such that the SMT solver can prove that f has this type using purely uninterpreted reasoning? And then we, in a second step, compare this blue type to the yellow type using more traditional programming languages techniques. So if you're familiar, we check that the arguments are related in a certain way, and that the return values are related in a certain way. And if all these sub-goals are indeed satisfied, then we discharge this overall subtyping obligation. OK, so to make this a little bit more concrete, let's return to our obligation from earlier, where we're asking, is the function negate a subtype of num arrow num? Now, because we gave this annotation to negate earlier, this blue type, the SMT solver can prove that f has this blue function type. So then we open up this function type and now compare, does the blue arrow type relate to the yellow one? And again, we check, are the arguments related in a certain way? Are the return values related in a certain way? And since all of these sub-goals are satisfied, in the system, negate is a subtype of num arrow num. OK, so at a high level, what's going on here is that the subtyping algorithm carefully factors the work into decidable SMT-based reasoning, and then more traditional, precise syntactic subtyping. So the upshot here is to get the best of both worlds by factoring the work that the SMT solver can do well, but then using more traditional techniques for recovering precision. And the kind of last challenge is proving that what we've done here makes any sense. And the kind of typical proofs that one would want for a system like this require that the logic is an oracle that the type system can refer to. But because we're introduced this nesting here, there's a circularity now that prevents the typical proofs by induction from going through. And so to overcome this challenge, we introduce a new proof technique whereby we stratify the type system into an infinite hierarchy. And then each of the systems at each level satisfies a traditional proof property. And then the type system is thought of as the infinite union of all of these type systems. OK, so that's a high-level intuition of how to overcome the challenges of nested refinements. And really, the takeaway is that this is the key to encoding dictionary-style objects that you find in languages like JavaScript. But I want to point out that even statically typed languages have dictionaries. And so these kinds of techniques will apply just as well there. OK, so there's several additional techniques that I've developed to overcome the rest of the challenges that I'd be happy to talk about offline with you if you're interested. Now, although the techniques that I've worked on so far target the syntax of JavaScript, I'd like to point out that other dynamic languages like Python and Ruby also have many of these same features. And so these techniques are applicable in these settings as well. And the last couple of challenges here are more JavaScript specific. OK, so that's a little bit about what are the kind of key ideas in the system. Now I'd like to talk about how I've started to evaluate the kind of usability and expressiveness of the system. And so to start, I chose 13 small but tricky examples from a popular programming book called JavaScript: The Good Parts, and a couple of benchmark suites. Now, the first thing to note is that the benchmark suite here is very small. It's about 300 lines of code. And the annotation burden is really high. It's 33%, which is a lot more than the 0% that was there before. But I want to point out that these benchmarks are really chosen to stretch the kind of expressiveness limits of the system, and in some sense represent an upper bound on how bad things can get. So I've also started to port examples from a related project on JavaScript. And in this case, the annotation burden is a little bit better. It's about 20%. And I've also ported a couple of examples from the Google Gadgets library where the annotation burden turns out to be much smaller. And in these examples, there's just a couple of object and array types that the programmer writes down at the top. And then most of the functions are operating on them in pretty straightforward ways. And so I expect that most client code won't be doing very, very tricky things and will fall into these fragments where the annotation burden isn't overbearing. So overall, the kind of annotation burden for these examples is about 12% with a really large variation. But this burden is already significantly improved by some pretty simple efforts to do type inference. And so in particular, there's still lots of room for improvement to develop more state-of-the-art type inference techniques here. So in particular, I'm starting to do more kind of state-of-the-art techniques to reduce this annotation burden. And one idea that I have for taking advantage of the fact that dynamic languages often come with a lot of test cases is to take advantage of these test cases and run them and try to predict, based on the runtime executions, what appropriate static invariants are. I think this will be an important way to migrate programs that have already been written without annotations in mind. And so as these techniques continue to improve, it'll be much easier to test larger and more varied examples much more quickly. Now, on the performance side of things, this benchmark suite takes about 32 seconds to run, which is rather slow for such a small benchmark suite. But I want to point out again that this number is already significantly improved with a number of simple optimizations. So trying to avoid making too many calls to the SMT solver when possible, and also identifying common patterns of programming where we can do less precise reasoning when the program actually doesn't require the full expressiveness of the system. And again, there's plenty of room for improvement along this direction as well. OK, so that's a little bit about how to use refinement types to handle some of these tricky features. I'd like to switch gears a little bit now and return to this notion of security for JavaScript programs, for example, like the kind that we encountered in browser extensions. And so recall our notion where we have a bunch of sensitive APIs on our client machine, and we have an extension framework. And our goal is to allow good extensions to do good things and prevent bad extensions from doing bad things. So what do existing browsers have to say with this respect? So what end of the spectrum is the Firefox approach, which essentially allows extensions access to all resources. So there's really very little that an extension cannot access. Slightly better is the Chrome approach, which allows extensions to access some resources but not others. So for example, we can say that an extension can access the DOM, but cannot access the history. So this is certainly a step in the right direction, but these policies are still rather coarse-grained and don't give any useful information to the user. And the user is basically trained to accept whatever permissions a particular extension is requesting. And so we're talking about browser extensions here, but other app platforms where we're loading untrusted applications, for example, on smartphones, also have a similar situation where the coarse-grained nature of the policies doesn't really give very much guarantees to the user. And so what we would like are much more fine-grained policies. For example, for our print New Yorker extension, we might wish to say that it can write anchor elements, but only the href attributes of those elements. Or if we wanted to be more restrictive, we might want to say that it should only be able to make those modifications when the original URL starts with newyorker.com and when the original URL is a prefix of the new one. And so to support these kinds of fine-grained policies, in addition to the kinds of security mechanisms that browsers already provide, I think we need to start integrating with languages at a much finer granularity. In particular, because we've built this foundation of expressive static reasoning using logic, what's really cool is that we can start to encode a variety of security properties within logic and then use this kind of framework to check, does an extension satisfy one of these policies? OK, so the ideas that I'll present right now of using refinement types for security are not something that I've come up with. Many researchers have been studying this idea. But up until recently, these techniques have applied to simpler programming languages, like functional languages. Now with the work on doing verification directly for JavaScript, we can start to combine these two approaches and start to do fine-grained security directly on JavaScript programs. And this is a line of work that I think will be really exciting going forward. OK, so the story is as follows. That a developer writes the extension along with an extension, along with a fine-grained policy authored in logic. And then the static verification system, like Dependent JavaScript, checks, does the extension actually conform to that specification? If so, the security expert then reviews the policy and then decides whether it's fit to publish to the App Store, for example. At which point, the user can then read one of these informative fine-grained policies and then decide whether or not to install it on his or her machine. OK, so the way this works is, in the first step, we take all of the sensitive APIs on our machine, on the browser, for example, and use refinement types to control how the API functions can be used. So for example, the network request function normally takes some URL to contact, and then sometime later returns back a string. Now we would require that the extension contact only URLs that are on some whitelist of URLs. The JavaScript eval function, which normally takes a string to parse and evaluate, now we would require that the extension only tries to evaluate strings that are not tainted, where strings that come back from the network are considered to be tainted. The getAttribute function for the DOM normally takes an element, an attribute to read, and then retrieves the value stored at that binding. Now we would require that the extension have the canRead privilege to access this particular attribute. And similarly, the setAttribute function, which normally would take an element, an attribute to modify a new value y to store, and then would actually perform that update, now we would require that the extension have the canWrite privilege to make this particular modification. So in this way, we go through all the API functions and use refinement types to mediate or control how they're accessed. And the second step is to type check an extension along with an extension-specific policy. And so as a flavor of the kinds of policies we might express in such a system, for example, a simple policy might say, for all URLs that are not equal to evil.com, then that URL is on the whitelist. And so in this way, we're encompassing the notion of a finite blacklist and treating all other URLs as safe to contact. And so now an extension that programs against this policy that tries to request a response from evil.com will be rejected because it doesn't conform to the policy. Instead, if the extension tried to request some arbitrary URL, where URL is some string that may or may not be blacklisted, again, we would statically reject this call because it's not definitely on the whitelist. Instead, if the extension first dynamically checks, is URL definitely not evil.com? Well, this time, because we're on the then branch of this conditional, we know from the policy that the URL definitely is on the whitelist in this branch. Now this particular request is safe to make. But then if the extension tries to evaluate the response that it gets, well, the string s that we get back here is either tainted or untainted. We don't know. And so it's unsafe to make this call to eval. And so instead, if the programmer first called a dynamic sanitization routine, which let's assume returns to us a string that's not tainted, now it's safe for the extension to evaluate this response. And so in this way, we can verify that this particular extension conforms to the policy. And so there isn't any need for additional dynamic checks at runtime. So this particular policy will not violate the policy that's defined for this extension. As another example, we might say that the URL newyorker.com is on the whitelist, and maybe golf.com is on the whitelist. And then we might say that for all URLs that are on the whitelist, then when you make a request to the URL, what you get back is not tainted. And so this captures the notion that we're trusting that whitelisted servers will return to us strings that are safe to evaluate. So in this case, now an extension can contact one of these whitelisted servers and evaluate the response without any need to sanitize. And again, we can statically verify that this particular extension conforms to this policy. And as a final example, let's return to our print New Yorker extension from earlier, where we might say that for all elements in URLs, if the original URL is stored in the variable old URL, and newyorker.com is a prefix of old URL, And if old URL is a prefix of new URL, then the extension has the can write privilege to make this particular modification. And so to type check this extension against this policy, the security critical operation here is this call to set attribute. And so if we take these arguments and substitute them back into our policy, there are 3 sub-goals that need to be satisfied. The first is the original value of the attribute stored in URL, which we can prove by giving a precise type to the getAttribute function. The second obligation is newyorker.com a prefix of URL, which we can prove by giving a precise type to the regular expression matching function. And the final obligation is URL a prefix of the string concatenation, which we can get by assigning a precise type to plus. And so because each of these 3 requirements is satisfied, the extension does have the can write privilege to make this particular modification. And so again, we're statically verifying that this extension conforms to this specific policy. Now instead, if the extension tried to write evil.com everywhere, if we substitute this back into our policy, the original 2 sub-goals are unchanged, and so those go through just fine. But now there is no way to prove that URL is a prefix of evil.com. There's nothing in the source program to relate these 2 strings, and so the system statically rejects this call to set attribute because it does not conform to the original policy. OK, so to start to demonstrate this kind of idea, I've taken examples from a related project where they use this approach to write provably secure browser extensions using the functional programming language OCaml. And so I've started to port these examples into Dependent JavaScript, which is about 400 lines so far. So these are obviously very kind of small proof of concept kinds of examples. But the idea is that well-typed programs not only don't have runtime errors, but they conform to the security policies that have been defined. OK, so that's a little bit about the kind of idea of using refinement types to track fine-grained security in JavaScript programs. I'd like to wrap up with a number of future directions of work that will help flesh out this goal of a more rigorous foundation for the web. So dependent JavaScript is an important step towards this goal. And certainly there's more work to do on inference and performance, like I've mentioned earlier. But one exciting opportunity is that I've positioned dependent JavaScript to be more usable than more heavyweight verification techniques. But there's several kind of more lighter weight tools like Microsoft TypeScript, Google Dart, et cetera, which don't provide sound guarantees, but they do a little bit of static checking to find certain classes of bugs and give a little bit of IDE support to the programmer. And these tools are becoming popular because they do give value. And so I think it'll be interesting to define translations between programs written in TypeScript, for example, into dependent JavaScript to give these users additional guarantees and additional IDE support when TypeScript fails to give them what they want. And furthermore, it'll be interesting to translate these techniques in DJS down to the more heavyweight verification techniques to do even more kind of checking. Now, another direction of work will be building up rich IDE tools to give to web developers. Because tools for JavaScript and other web technologies really lag behind the kinds of tools that Java and C# programmers are used to, for example. Now that dependent JavaScript provides a foundation for static reasoning about JavaScript, I plan to build software engineering tools to do traditional things like code completion, refactoring, et cetera. And I plan to design these tools in a way to have web-facing interfaces to make it easy to collect data about how programmers use JavaScript, and also the kinds of errors that they run into with these kinds of tools to help build tools that are more usable in practice. On the security side of things, there's a lot of future directions of work. So one is that although logic is a great specification language because it's so expressive, well, one downside is that in this model, we're asking the developers to write fine-grained policies, and we're asking the security experts and users to read these fine-grained policies. So to make these assumptions a little bit more realistic, one idea to help developers is, again, to take advantage of the fact that a lot of extensions, for example, exist. So can we mine these executions to try to identify ways in which extensions typically interact with APIs, and use this as a way to bootstrap and infer policies for good versus bad behaviors. I think it'll also be important for platforms to offer an incentive to developers. For example, an extension that can perform its functionality with relatively low privilege should be ranked higher on the page than a similar extension that requires access to your social security number, for example. In terms of security experts, they're certainly in a position to be trained to use tools to help them. But I think it'll be important to develop modeling tools to analyze how different policies for different extensions interact with each other, and whether or not they satisfy some more platform specific goals. And in terms of users, one idea is to use concrete execution traces to identify how a policy either admits good behaviors or what kinds of behaviors it rules out, to give the programmer a much more concrete sense of what these policies mean. And again, I think it'll be important for community services to do the bulk of the burden of reviewing these policies and then recommend extensions to users on their behalf. Now, as much as possible, we'd like to statically verify properties, but at some point we do need to integrate with dynamic checking as well. Because for example, this untrusted code might use dynamic code loading to get more code at runtime, and unfortunately it's impossible to statically analyze code that we don't have yet. And so to handle situations like this, we really do need to integrate with dynamic enforcement. Now, dependent JavaScript can support this in the following way, in that it's flow sensitive, in that we can establish some, let's say, old type specification before this call to eval. And we can imagine extending the system with the ability to write an assumption about what new type specification must hold after this dynamic code loads. And so for the purposes of analysis, we can use this new specification for the rest of the program, and then at runtime check, does the program that's actually loaded satisfy this assumption? And so one way to do this is to fall back on dynamic checking. But again, we'd like to try to avoid this kind of performance overhead when possible. And so one idea that I think will be useful here is to explore something that I call staged analysis, which I explored in a prior project, where the goal is to come up with a lighter weight static analysis that's fast enough to run in the browser when the code is loaded, so that we don't need to resort to full-blown dynamic checking. And so I think this will be a promising way to integrate this kind of static and dynamic checking for JavaScript programs. And the last thing I'd like to talk about is what is the trusted computing base in this workflow. Because notice that here the security expert reviews only the policy because it's trusting that dependent JavaScript correctly checks, does the extension actually satisfy that policy? Furthermore, tools like dependent JavaScript depend on SMT solvers to correctly answer queries. So ideally, we'd like to eliminate these two forms of trust. So in a prior work on a related refinement type system, I showed how to remove the SMT solver from the trusted computing base in a style similar to proof carrying code. And so I plan to apply these techniques to this setting as well. And kind of going forward, as these techniques mature and become really important, we can eliminate dependent JavaScript from the trusted computing base using more heavyweight techniques like full formal verification, like the kind of techniques my friend Zach described a couple of days ago. So going forward, I think there's a lot of exciting directions for work that will lead to this goal of a more rigorous software foundation for the web. Now, in particular, I've talked a lot about static types for reliability, in particular security, and development tools. But there's also this kind of third promise of static type system, namely performance. And indeed, I think dynamic languages are, by default, they're rather slow because of so many dynamic type checks. And modern browsers do a lot of just-in-time optimizations in the compiler to make these things run fast. And so I think there's opportunity for additional precise static analysis to enable additional classes of optimizations, and in particular as they relate to custom architectures. For example, some of the work here at UW on designing custom architectures for mobile devices, for example, where you can't afford necessarily to spend as much time and energy on a full JIT compiler. And so by using these kinds of analysis techniques, we can target more custom architectures like this to run these programs more efficiently. OK, so I've talked a lot about refinement types, but more generally, I'm interested in programming language techniques. And so in prior work, I showed how to use something called set constraints to do program analysis for dynamic languages like JavaScript. And I've also started to look at using runtime instrumentation to help analysis for these kinds of languages. And in prior work, I showed how to do Dataflow analysis for concurrent programs by using a race detector in a careful way to reduce the kind of effort for the analysis writer. And going forward, I'm certainly interested in exploring a variety of language techniques and how they can improve reliability and correctness across a wide variety of domains. OK, so to wrap up, I've talked a lot about why scripting languages like JavaScript are pervasive and therefore important, and why they're hard to reason about. And I've given a flavor of how in my recent work, I've developed new static reasoning techniques to overcome these challenges. And one of the reasons that I'm excited about this line of work is that I think it'll lead to a platform for doing fine-grained security for programs on the web. Thanks a lot for your attention.
So we have time for questions? Yeah, constantly.
So you gave that example where you loaded a URL and changed it and so on, right? And you could check that it actually was that website because he had that regular expression right in front of it. I mean, there could be some Turing complete computation going on. Are you maybe trying to, or thinking about allowing the user to give you a proof certificate or something like that, that actually this URL must be correct or something like that?
Sure, so the question is, in the example that I gave with the print New Yorker, the kind of URL and the regular expression were statically defined, and so it was easy to prove. How do you handle more kind of arbitrary computations? And the kind of approach that I'm taking in this work is to try to define a common framework where you can verify as much as you can statically, but then resort to dynamic checking when you have to. And so you can imagine for more complicated properties that are either beyond the reach of static reasoning or just can't be specified because you don't have all of the code yet, for example, integrating with dynamic checking for more complicated cases like this.
I'll ask a question
Sure.
since I have the microphone. From your experience in playing around with these more fine-grained security policies, can you share even informally some sort of best practices? So in your New Yorker example, right, the policy you're really trying to write down is don't trick me into going to an evil domain. And you broke that down into make sure it's an A tag, make sure it's newyorker.com, only append. But there's a thought process that gets you from the intuition to the policy you write down.
Right. Yeah, so that's a good question. And so this is certainly very much in the early stages, like I said, they're very kind of toy benchmarks. And I think going forward, what will be important to identify these kinds of patterns is by taking advantage of the fact that things aren't perfect, but people run a lot of extensions in untrusted code, and not all of them do terrible things all the time. And so the idea is to take these kind of existing extensions, the ones that are popular, for example, and try to monitor the ways in which they use APIs to try to find patterns of maybe the ways in which they access particular elements on the page, and use this as a way to bootstrap this kind of policy specification language. And so I think patterns will certainly emerge, as we kind of run those experiments.
Yeah, so a couple. A lot of things where we ask users to do stuff, we run into problems of either people won't pay attention. I think I suspect a lot of the complaints about Vista is it put a lot of those things in the user's hand, didn't know what to do with it, and just so what would be your? You said a little bit, maybe this is along the lines of that previous question. What would be your way of saying a browser writer is going to say, if you're going to be an extension to my browser, you have to satisfy these properties, and how would you use what you've done so far in order to make that kind of thing work?
Sure, so yeah, you're absolutely right. The kind of more work that an extension developer or anybody has to do will necessarily limit how practically it'll be adopted. But I think a lot of the kind of work on trying to infer common cases as much as possible will reduce that burden. So hopefully the programmer doesn't have to write too much manual kind of security specification. But again, incentives in terms of giving particular extensions better rankings or better ratings on the page, or allowing those extensions to run more quickly, or giving them particular capabilities that unverified extensions don't have, are all ways in which you can imagine incentivizing a system where the developer does have to go through a more rigorous verification pipeline before being posted to the App Store.
So in the statically typed language world, there are quite sophisticated type systems. I'm thinking about parameterized types and type classes in Haskell and so forth. Can these ideas be translated over into that your domain?
Certainly. So the kind of prior work on refinement types typically are in the context of statically typed languages where you're trying to track additional, more precise properties. In this work, I've kind of used the techniques to try to recover even simple typing properties in languages like JavaScript. But there's nothing in the kind of approach that I've taken that precludes applying to languages like Haskell and other kind of statically typed languages. The fact is that to do reasoning for a dynamic language, it turns out you need to use kind of more heavyweight techniques than in a traditional language because you don't even have base types and things like that to begin with. But you can imagine using a lot of these same techniques in traditional statically typed languages as well.
All right, let's thank Ravi again.